Ladies and gentlemen, and everybody in between, of course, also, welcome back to another week, or the first week, actually, the first real week of advanced data mining and machine learning lecture. So this week, we are going to talk, or have a kind of flashback. We're going to talk about the basics, the methods, the tools that you got to know. Most of you probably got to know in KDDM in the lecture by Matthias Renz last winter semester, or the year before, or whenever. So of course, as I told you last week, this lecture will somehow be on top of this, and since I want to be somehow self-contained, I'm going to show you the real basics, so to say. But for those of you who already attended KDDM, I have some kind of additional things on top, so to say. Yeah, so I will give you some more methods, some more tools here and there that have not been handled or have not been addressed by Matthias Renz last year, last semester, whatever. Yeah. Okay, so let's see what's coming up. We will talk about, first of all, about the basics, of course. We again somehow reiterate about these kind of canonical representations of feature vectors. And then we will go just through all of those different tasks that you can have in data mining and machine learning. So clustering, classification, regression, frequent patterns and association rules, outlier detection. Of course, this is a mix of supervised and unsupervised tasks. Yeah, we'll have a look at all of those, about the basics, the basic tools and the basic challenges, pitfalls, whatever. And also, as I told you before, some kind of new things that are somehow also basic. So in my point of view, it should be in your basic toolbox. So after this week, after those podcasts that are ahead of you this week, I hope you have a real good basic kind of toolbox where you can really do some cool fancy stuff with feature vectors. So let's jump in. Okay, once again, overview of the major KDDM topics, of course, are the basic methods on unsupervised learning tasks, clustering, outlier detection. Outlier detection can also be supervised, of course, if you have labels, but very often it's unsupervised. And of course, association rule mining, yeah, and frequent pattern mining, of course. Unsupervised means you don't know anything about the data, no labels, nothing at all. You just have the data. And supervised methods, you have some labels, you know already the outputs for a couple of data, that's your training data, and now you want to derive a model in order to predict new data which is coming in, which has no label so far. So in that case, you're talking about classification. If the output, the label is a category, yeah, categorical, and if the output is numerical, meaning a number, it's called regression. No? And we talked about that last week. Most of the methods covered by KDDM. Typically, I'll assume that the data is in a specific type of format, type of representation, a canonical representation in that case, which is feature vectors. Yeah, so tables of objects, and the columns, the types of the columns are typically floats, yeah, or doubles. Yeah, so numbers actually. So let's have a look at what actually feature vectors are. Well, typically we need a domain, which is a set of objects, semantically related objects, yeah, which is called DOM here, and a similarity measure, or more often a distance measure, which is more or less intuitively the other way around, but always keep that in mind, that a transformation from a similarity of a given similarity measure into a distance measure is very often not always so easy. Yeah, so because the ranges are a little different. So if you're talking about a distance measure, a distance of 0 means they are perfectly equally, perfectly similar. Yeah, and what is the maximum distance of absolutely dissimilar objects? On the other hand, if you're talking about a similarity measure, a similarity of 0 means they are totally unsimilar, yeah, totally distant, or dissimilar. And what is the most similarity what you can have. So they have completely different ranges, and somehow at least semantically different ranges. So a transformation is not just 1 divided by something or 1 minus something, so always keep that in mind. Anyway, very often we have a distance measure, dist. And that's it actually. So the domain is typically, in that case, as you see down here, the canonical feature space, which is also a metric space. Well, when first of all, okay, one step after another. So a feature vector or feature vector space. Feature space is a metric space if the distance measure is also a metric, meaning that it is reflexive, positive, definite, symmetric, and does meet the triangle inequality. And then in that case, we have a metric feature space, and the canonical metric feature space, of course, is the one that is R to the power of D. That means the objects have only numerical features, D numerical features, meaning that the objects are somehow points in a D-dimensional space. So if D is 2 points that are points on the plane, if D is 3, then we have the objects as points in a 3-dimensional space, and so on and so on. And then of course, if you think about points in some space, you can think of a distance between the points as the airline distance, which is nothing else than the Euclidean distance given below here. So that is the most canonical feature representation, feature space. This metric property, a lot of people make a lot of noise about this metric property, that is so important and stuff like that. Well, actually, in practice, it's not. So very often you work with distance measures that are pseudometrices, meaning that they have not in all cases the metric properties for all possible observations, for all possible objects, but usually you don't care. Most of the time, the distance measure, so pseudometrices, act as or appear as matrices, but not always. You cannot assure that for always, and very often you don't care too much about it. So many people always say, metric spaces or metric distance functions are extremely important for, I don't know, some measures or whatever, or for some methods, or for some algorithms. But in the end, if you really think about it, it's not really the case. So if you think that your distance measure, if you come up with a specific distance measure for your data, we will see that a lot in this lecture, where we talk about different distance measures for specific complex object representations. If this metric property is not fulfilled, then very often people don't care about it, more or less.